Let's now take a look at projectile motion. As far as extension 1 motion goes, then we consider two-dimensional motion of a particle projected into the air, subject to gravity only. In other words, no air resistance. When we come to looking at it in extension 2, we might throw that in as well. We might have to talk about air resistance. As far as extension 1 is concerned, gravity is basically the only force, or the force due to gravity. So in other words, if I look at the accelerations, what do we know? In the horizontal direction, as far as we're concerned, nothing is happening. There's no resistance, it's just nothing happening. The acceleration due to gravity is acting on the particle. We tend to, for projectile motion, define up being positive, so therefore the gravity is acting in the opposite direction, it's negative, and it's purely in the vertical direction, as we say, so it's minus g. Initial conditions. So when t equals 0, we're going to project with some velocity at some angle to the ground. So here we go, off we go. So that would be the vector initially. Obviously it will change as time goes. But let's have a look at this vector. Its magnitude is v, we're saying. That's what the velocity is. But we could have a horizontal and a vertical component and make some angle with the ground. A little bit of trig, we can work out the initial conditions both horizontally and vertically. So horizontally it's v cos theta, vertically v sine theta. But as I say, it'll move, and that velocity vector will change depending on where it is. So a little time later, there it is, makes an angle with, let's call it alpha, with the ground. A bit later, it'll get to the top, and it just goes horizontally when it's at the top, as far as velocity is concerned, and it'll start coming back down, and so on. But if we were to draw the space curve in, we'd see it carves out a parabola. And for the sake of this problem, we're saying it starts at the origin. Now, of course, it might not start at the origin. We might set it at the top of a cliff or something like that. But for the sake of this, we're saying, well, origin. Most of the times we're there. Oh, one thing to note, if you ever need to work out maximum range, because we're saying there's no resistance, and because the parabola is nice and symmetric, we know the maximum range will always happen when that angle is 45 degrees. 45 degrees will give us the maximum range. Okay, let's go and work out some components. Remember, all we know is acceleration. Now, to make life a little bit easier, I've said acceleration is 10, a nice neat whole number. Sometimes I'll say it's 9.8, of course, whatever number they give us. Sometimes we just leave it as g. Okay, I'll use minus 10 for this. Okay, I want to integrate. So when we separate the variables on this one, if we multiply by the t, if you like, with 0 times the t is 0. So I just get that this integral is 0. The initial condition we set horizontally was v cos theta. We want to come up with an expression for velocity. So integrate that, substitute in, and there we go. Now that kind of makes sense, because look, it's still v cos theta. Remember we said there is no acceleration happening horizontally. So it's constant. It's whatever that initial velocity is horizontally, it's going to stay like that. And that's what we've now found. Well, what happens in the vertical direction? Separate those variables out, do a bit of integration. There's the initial velocity v sine theta, but now we're taking away 10t. So what's that? Well, that's the effect of the gravity. It's slowing it down, because we're going up. It's slowing it down. Every second in this case, we're taking off 10 meters per second off that velocity. If I was to write out the velocity vector then, it would be whatever the magnitude of that vector is, cosine theta in the I direction, and then the magnitude of the vector sine theta minus 10t in the j direction. Let's work out equations for displacement. So again, separate out the variables, because velocity is dx dt in this case. And we get vt cos theta. Over in the vertical direction, integrate vt sine theta minus 5t squared. So we've ended up with a whole heap of different equations which we should be able to use to solve any problem. There is the displacement as a vector. Some common questions they like to ask with projectile motion. When does the particle hit the ground? Oh yeah, that's kind of something you might like to know, because I'm going to fire it off. Well, when does it hit the ground? How would we answer it? We think about what's happening. Well, it's going to hit the ground, assuming I've projected from the ground, of course, when y equals 0. Now, if I started at the top of the cliff and I made that the origin, then I might hit the ground when it's negative whatever the height of the cliff is. Might be more convenient to make the ground always equal to 0, and in that situation start with a height of whatever the height of the cliff. Up to you how you deal with that. What's the range of the particle? Well, that's how far did it go. So I need to know when it hits the ground. Once I know the time, I could substitute into the x component, and that would tell me how far it went. How high did it go? What was the greatest height? Well, what do we know about the particle? It's going to go up, it's going to stop, and then comes down. Well, it's that stopping that's the key point. So we'll find, when does it stop? When is that vertical velocity equal to 0? It's no longer going up. Find that time, but then substitute it into the y component of the displacement, and it'll tell me how high it goes. What angle does the particle make with the ground? So when it hits, what sort of angle is it hitting at? It might not necessarily be the ground. Sometimes they might say, well, what angle is it making after 5 seconds or something like that? Okay. Well, we have to find, in this case, when it hits the ground. Remember I said, if you want to find the direction, it's the velocities we work with. So I'm going to need to substitute into the y dot, so the vertical component of velocity. The horizontal one is, of course, constant. And then I know, oh, well, the tan of theta will be y dot on x dot. Solve that problem, I can get the angle that it hits the ground. But basically, to summarise, when we're talking about projectile motion, what do we know? We don't know a heck of a lot. We derive most things. We know it's going to start with these accelerations, and this time in the vertical I've called it minus g, whatever gravity's been set at. We also know the initial conditions of the problem. So yep, v cos theta, v sin theta. The displacements are whatever we've set them at in the problem. That's pretty much it. With that information we can now go and solve most problems. Let's do a simple little example. A ball is thrown with initial velocity 25 metres per second, makes an angle of whatever the inverse tan of 3/4 is. Work out greatest height. Work out my initial conditions. I'm drawing up the triangle to work out our cosine and sine ratios. If that angle has an inverse tan of 3/4, opposite over adjacent, 3/4, hypotenuse is 5. So now I can substitute in. V cos theta ends up being 20. V sin theta ends up being 15. Okay, I start with the accelerations and work my way down. Okay, I'm going to integrate. Separate the variables. So I'll work on the horizontal one first. This time the initial velocity is 20, sub in. Guess what? It stays 20, and that's what I'm expecting. I'm expecting that constant 20. Over there in the y's, and 15 minus 10t. Let's now go and find our displacement equations. Over in the horizontal direction, we get 20t. In the y direction, 15t minus 5t squared. We have our equations. Let's go solve our problem. And our first problem was find the greatest height. Okay, write these things down when you're doing a solution. You want me to find that? Okay, I know that's when the vertical component's equal to 0. Solving that, okay, it's after 1.5 seconds. Sub in, we get 45 on 4. Interpret the answer. I'm probably not going to write 45 on 4. Probably has more meaning if I say 11.25 metres above the ground. No, it doesn't matter. I mean, it can say 45 on 4. Range, what's the range of the particle? Oh, well, I now know it hits when it's 3 seconds, because we're talking about a symmetric, no air resistance. We projected from the ground, we're landing on the ground. So for that reason, the time it went to go up is the time it's going to take to go down. I don't need to do any more calculations. I can just simply go, well, time of flight's 3 seconds on this one. But be careful with that. Make sure if you are doing that, yes, you're projecting from the same level that it lands at. There is no air resistance. It's beautifully symmetric. Sub in, and we get 60. So there's our range. Velocity and direction of the ball after half a second. Horizontally, we know it's 20. Vertically, we want that velocity, it turns out to be 10. Draw up a triangle. I know it's going up, because remember we said it reached the top after 1.5 seconds. So now I've drawn it right, it's going up. A bit of Pythagoras, the hypotenuse is 10 root 5, so we know the magnitude of our velocity. And a bit of trig, there's the angle as well. Okay, it's going at 10 root 5 metres per second, and an angle of 26 degrees 34 to the horizontal. Let's have a look at a couple of HSC questions. A couple of years ago, this was an interesting little problem. So we've got a game we're designing here. So the player will reach one side of the pit. There they are over here. Projected here. And must shoot a projectile to hit a target on the other side of the pit in order to be able to cross. So I guess if they hit it, some bridge opens up or something like that. Across they can go. However, the instant the player shoots, the target begins to move. That's the second bit of motion they're talking about here that they've labelled U. So they're here, they're going to shoot to try and hit this target, but the target is moving as well. It's moving at a constant speed, and that constant speed is half the initial speed of the projectile. Okay. As shown in the diagram. Typo. The initial distance between the player and the target, which is the width of the pit, is d. The initial speed of the projectile is 2u, hence why they labelled this as u for the target moving. We're taking g to be the acceleration due to gravity. The launch angle is the only parameter that the player can change. So in the game they can change the angle that they're going to shoot at. Everything else is fixed. Taking the position of the player when the projectile is launched as the origin. Okay. The position vectors for our projectile and the target have been given to us. So we don't have to work these out. They've given it to us. Okay. Show that for the player to have a chance of hitting the target, D must be less than 37% of the maximum possible range of the particle. Now the thing about this, it was one of those questions that has not been scaffolded. It's just like, here is all the information, go solve the problem. What can you come up with? Alright, okay, well, first thing I did, I said, well, when's the projectile going to hit the ground? That's totally independent of the target or anything. I'm just firing a projectile, it's going to hit the ground on the other side. So let's find that. We know it'll be, well, I don't know anything about the horizontal displacement. I don't know anything about that. But I do know that the vertical displacement will be 0. So I can change my vector to be that when it hits the ground, that displacement vector. But hang on. What we're basically saying is this 2ut sine theta minus g on 2t squared must be 0. We're saying the horizontal component of the displacement vector of the projectile is 0. Two possibilities, only one of those ends up making sense. T equals 0, well of course, that's where we started. We started at the ground. So the other one must be when it hits the ground on the other side. So 4u sine theta on g. Okay, I've got that bit of information. I know when the projectile hits the ground. How far away is that then? What's the range of this particle? So now I'll go and substitute it into the horizontal component of displacement. Sub it in for t, and I end up with this, and I just thought, looks a bit neater. Look, I've got the sine theta cos theta. I might make that just one trig function. So I use my double angle results there. There's 4u squared sine 2 theta g. But I'll tell you what it does do. I can now work out the maximum range. Now, remember I said it's when it's 45 degrees, but the other way you could look at it and say, well, it's got to be when sine 2 theta is 1, and that's sine 90, that's when theta equals 45 degrees, and that's why 45 degrees will give you the maximum range. What about the target then? Where's the target at this time? Because that's what I'm trying to hit. That's fantastic, that's when it hits the ground. But I wanted to hit the target. So the target started d away from me, and it was travelling at a velocity of u. So it'll be u times this time we've just worked out. That in fact was, if we go back to it, there you go. That's what we were told in our displacement vector. Horizontal displacement was d plus ut. So it's d plus 4u squared sine theta on g. So in other words, if I'm going to hit the target, then the displacement of the target would have to be less than or equal to the range of the projectile. Because if the range of the projectile was less than the range of the target, there's a chance that when I hit the ground, it's too far, the target's gone. So I need that. So what we're saying is d plus 4u squared sine theta on g must be less than or equal to 4u squared sine 2 theta on g. Making d the subject, I now know this. d has to be less than or equal to 4u squared on g sine 2 theta minus sine theta. Remember, the only thing we can vary was theta. So the u squared's not changing, the g's not changing. So it's that little function inside the parentheses that's controlling the distance. And if I want that distance to be maximised, then sine 2 theta minus sine theta must be maximised. What's the biggest that could be? So I create this new function. Sine 2 theta minus sine theta, differentiated, because I want to maximise it. When are the stationary points? Get them, finding the maximum point of this function. Cos theta is 1 plus or minus the square root of 33 on 8. Yep, they've made the numbers real nice for us. I know theta's got to be an acute angle because we're firing this projectile off, so I can discount the negative case. 1 minus root 3 can't be that. So I know cos theta is 1 plus the square root of 33 on 8. It's approximately 8.8431. Sine theta, therefore, sine squared would be 1 minus cos squared, so sine theta will be the square root of this, 0.5378. So what happens to d now? We said d was less than or equal to 4u squared on g. No, there. Sine 2 theta minus sine theta. Well, guess what? I've now converted that back to 2 sine theta cos theta. Maybe it wasn't a smart thing to do, turning into, so I could substitute in sine theta and cos theta. I've turned it back. We get 0.3690. Hang on. 0.3690. That's 37% basically. So yes, D has to be less than or equal to 37%. That's what last year's what they did for this one. This time we've got 2 particles being projected at the same time. Different angles though. So what's happening? B is being projected horizontally. Down it comes. A is being projected at this angle of theta. The position vector has been given to us for both particles. So this time we've got that. We don't have to do that work. Thank you. Angle theta is chosen so that tan theta equals 2, and we know the particles end up colliding. They will occupy the same position at the same time at some point. By first showing that the cosine of theta is 1 on root 5, verify that V is the square root of 5 times u. Well, tan theta is 2. We've been given that information. Draw ourselves up a little triangle. Pythagoras. Cos theta equals 1 on root 5. Ooh, thanks for that. There's a nice little mark. Verify that V equals the square root of 5u. Alright, well, the particles collide. When they collide, we know their horizontal displacements are equal. I mean, the vertical ones will as well, but the horizontal ones are probably easier to work with this question. So in other words, Vt cos theta will be the same as Ut. But cos theta, we just said, is 1 on root 5. The t's will cancel, and there we have it. V is the square root of 5u. We've got our answer. Show that the particles collide at this particular time. We knew 3 things were the same when they collide. Their horizontal displacement, we just used that. Their vertical displacement and time. Well, time's what we're trying to find, so it must be the vertical displacements we're going to set to being equal. So when t equals this capital T, we know the vertical displacements will be the same. Sub all that in. So capital T went in for T. Okay, let's play around with this. We want to make capital T the subject of all this, and hopefully we'll get H on 2U. And yeah, it does. The root 5s cancel. We've got capital T. When the particles collide, their velocities are perpendicular. So we now have a bit more information. Show that H is 2U squared on G. Their velocities are perpendicular. This is where vectors are going to come in handy, because we know the dot product must be 0. So let's find the velocity vectors. They didn't give us those. Differentiate the displacement vector for A, differentiate the displacement vector for B. They're perpendicular, so that dot product must equal 0. Okay, we now have this. We keep going, and eventually playing around with it all, subbing in what we found for sine theta, subbing in what we found for cos theta. We also know V, we worked that out, so that can be subbed in as well. Eventually, we end up with this expression, u squared minus 2ugt plus g squared t squared. But that's a perfect square. So u minus gt squared is equal to 0. T equals u on g. Okay, but we've got to show h is that. T is u on g, but oh, hang on. H on 2u then is u on g, because remember we showed t was h on 2u. We've got it. Oh, but it kept going. Prior to the collision, the trajectory of the particle A was a parabola. I guess once they hit, it sort of went off in different directions. Find the height of the vertex of that parabola above the horizontal plane. Well, maximum height would give me the vertex. It's basically saying when does it stop, what's its greatest height, that sort of thing. So maximum height's going to occur when vertical displacement's equal to 0. So root 5u times 2 on root 5 minus gt is 0. T equals 2u on g, which is h on u. Now when t equals h on u, now let's find the vertical displacement, because we want to know how high it goes. Not a nice expression, but there it is. It satisfies the question. They said give your answer in terms of h. There it is in terms of h. 2h minus gh squared on 2u squared. Okay.